Do you want to do the introduction?
Well, you can do it.
I don't have any.
Yeah. So let me do it. Okay, so this Friday we're happy to have Diego to give us a whiteboard talk. So Diego graduated from Perimeter in 2022, and then he did his postdoc at Simon Center, Stony Brook. And recently, a few weeks ago, he moved to UCLA, second postdoc, and now he's going to tell us about some groundbreaking work about non-invertible symmetries.
Thank you very much. Thank you for the introduction. Thank you everyone for being here. I'm very happy to be here. It's a great place. It's a fantastic place to do physics. I've only been here for a couple of hours. I already had a very useful conversation. So I hope you all interrupt me with more questions so that we keep the conversation going. So I wanted to tell you about a paper that came out in the summer with Adar, Sharon, and Yunqin Zheng, where we try to say a few things about continuous non-invertible symmetry. And I usually like to begin with a quick summary of the main point of the talk, and that way, if you're not interested, you can decouple right away. So here is a summary. It's okay if you don't understand everything you say. I will explain what the different words mean during the rest of the topic. So the usual statement for continuous symmetries is Noether's theorem. This is the main tool we have for continuous symmetry. And what it says is that for every continuous symmetry, by the way, is this large enough? Should I, can everyone see in the back? Yeah, okay, good. So for every continuous symmetry, there is a conserved current. And vice versa. Okay, and everyone here is familiar with this statement and why it's an important thing. There are entire books written about this statement, and it's an extremely useful tool for understanding quantum field theory. And so what we try to do in the paper is a generalized version of this, which says that for continuous non-invertible symmetries, the same statement holds, except that now the conserved current is a twist current. If you have this word here, the theorem is still true, but you have to add this word here. And I will now explain what I mean by these things. Yes, please.
Yes, so just so I understand what you mean by continuous non-invertible, the non-invertible that I'm familiar with is just rational values.
So, yeah.
So here you're not considering rational values?
That is an open question. So we want something that is actually continuous. So our setting will not accommodate rational symmetries.
Right.
We want
that was my question, because the rational is that essentially discrete. There should be a conserved current. Right?
Yes, exactly. So there might be a generalization, an even bigger generalization that does describe those. Our generalization does not. So
you're going to have a continuous genuine continuous.
We only
with real values of the parameter alpha.
That's the only thing we can do for now. There might be a version of this that it's even more general, that involves rational things, but we don't have anything to say about that yet. Another question? No? Okay, so I want to explain what these two words mean here. And then we begin with twist. Give me a quick summary of what this means. Also, sometimes you will hear people call this a non-local. Or even a different. Okay. So everyone here is familiar with the notion of a bulk operator, a point operator, something that is phi of x, which is defined at a point. And there's also things like a line operator, like a Wilson line. Okay. But there's another class which is kind of in between, which is a twist or a defect operator, which is something that lives on a line. It's a general line. So this is something that depends on a point, but it's only defined on the world volume of something extended. And a simple example would be like in Yang-Mills, for example. You have the field strength. This is not gauge invariant.
So this is not a nice local operator in the field. What you can do is you take a Wilson line. An open Wilson line has like a free fundamental index, so that you can contract with one of these. And if you continue the line, that gives you an anti-fundamental index. So F on a Wilson line, that's a well-defined operator. So this is trace of F mu and then E to F. This is gauge invert, because the trace is basically in the vector and the coloring. So this operator on the line is well defined. It's not a whole thing, but it's a defect thing. So this is an example of a defect operator. Something that is only defined inside or within extended things. Okay. Now, to call something, this is a general defect thing, but twist more specifically, at least for me, twist. I'm going to reserve it to the special case where the line L is topological. Topological means that the correlation function for this, and if you deform it, is the same. So if you have a line operator whose correlation functions don't change when you deform it, we call that line topological. And for me, a twist field is going to be an operator that lives on a line that is itself topological. And so you can understand twist fields, twist operators are very similar to just local operators, but with branch cuts, where the line itself behaves like a branch cut. If I compute that, for example, a simple example would be if you have a fermion here, x fermion 0. This is something like square root of z. Let me call it z over w minus square root of w over z. Z over w. This has branch cuts, because if you take a fermion around another fermion, you pick up a minus sign. So you can think of a fermion as living at the end of a Z2 line.
Sorry, this is in 1 plus 1?
Yeah, this is a simple example in 1 plus 1. But more generally, any operator that is attached to lines, to topological lines, you can think of the topological line as defining a branch cut for the correlation function. So the correlation functions of twist operators are very similar to regular correlation functions, except that you have branch cuts. Okay?
I'm a little bit confused. So everything you said up until this example made a ton of sense. It's very interesting. But in this example, what theory is this? Is this
This is-
theory with
this is
gauge
preferred.
fermion pairs?
Preferred.
Just prefer. But then why are fermion operators attached to lines? They're not
It's a
attached.
Z2 line, it's -1 here.
But so then you're gauging lines.
No.
No.
In a regular free fermion theory, you can think of the fermion as living at the end of a fermion line, because if you take another fermion and you take it around, you cross the line and you pick up minus. It doesn't change anything, you know, it's just another way of saying that fermions have branch cut.
He's talking about the wrong. No.
Yeah, sorry, this is the wrong.
Oh,
Sorry, yeah.
oh, okay.
I didn't want to get into too many details, but yeah, this is the Ramon
Okay.
set. It's the Ramon sector operators.
Okay, okay, now I'm happy. It's okay. It's okay. Sorry to drag you, but it's okay.
So this is the first part of the main claim. If you have a conserved current, something that satisfies this, but J has branch cuts, call it a defect current, a twist current. Okay. It's a conserved thing, conserved vector, but it's only defined within the world volume of topological thing. Okay. So this is the definition of this. Now let me explain what I mean by this. Any questions so far?
So for you, the twist operators will always be lines, so you're always.
Not necessarily. Could be any extended.
But what you're talking about will work in the generic number of functions.
That's the hope. Yes. Maybe, yeah, that's a good point. Forgot to say this. This is, at this point, this is really a conjecture. And we only have a proof in 2D. We believe that the story is general. We don't believe that the two-dimensional case is really that important. we had some technical difficulties that in 2 dimensions, we could say everything very rigorously. We really think this should be general. There might be some subtleties that one should work out in the higher dimensional case. But at this point, we only have a proof. Actually, we only have a proof in 2-dimensional CFTs. If you remove the condition of conformal invariance, we still believe that the claim is also true. But if you want to be rigorous, we only have a proof in this case. Okay. Another thing that I forgot to say is that this statement here, we're not the first one to make it. It was already implicit in various papers. There's very important work of Ryan Thornton with Yifeng Wang, where they already anticipated that something like this should hold. Also, Zheng Xiao also made very similar claims that something like this should hold in various talks. And some concrete examples had also been worked out by other people. For example, Theo Jacobson has a very concrete example of something like this, which was super useful for us. And other papers that I'm forgetting right now. I'm not gonna mention many references, but if you want to know more, please do ask me.
But this was always in 2D, it was never in 4D.
Yes, it's always a claim in everyone that has made any claims. We are all very conservative and only make claims in 2D because that's the only case where we really have a good handle on the theory.
Yeah, because my understanding is that there is no continuous non-invertible in 4D. No.
Oh, there are, yes. No, there are known examples. Yes, there are. Yes, they're a little bit boring. I'm going to explain what boring means in later, but there are concrete, rigorous examples in 4D.
Oh, okay.
Yes. We don't know if, and they do satisfy this condition. We don't know if every example in 4D is going to satisfy it, but we do know that some examples do. Yes. Okay. So now let me move on to the non-invertible part of the claim. I'm not gonna give you the completely general definition because it's boring and it's not very useful. Instead, I'm gonna tell you about a very concrete example where things should hopefully be general enough. Let me take again 2 dimensions because this is where things are simplest. And let me take the simplest quantum field theory of all quantum field theories, which is Pi-4 theory. Let's take the usual 4, also known as the critical Isaac. This theory has lots of interesting things about it. Perhaps the thing that characterizes this theory is that it has its Z2 symmetry, which is just the spin up, spin down, which acts like this. Okay. And one straightforward consequence of this symmetry is that if you compute the 3-point function phi, it's in 0 because this is odd under the symmetry. But another interesting fact about this theory is that if you compute the 60 with pi squared instead of 5, turns out that this is also 0. And this is very confusing because it's even under this. So that it seems that there is no selection, no symmetry explanation of this selection rule. Okay? This is a very weird phenomenon that doesn't seem to have an explanation in terms of symmetry. I mean, you can try to think of all the symmetries of this system, and none of them is going to explain this selection rule. Now, it turns out that there exists an operator that I'm going to call D, which commutes with Hamiltonian, and that satisfies D of phi squared equals minus phi squared. So this operator does explain this selection rule. But this operator is a little bit weird because, for example, if you compute D of phi itself instead of phi squared, you get 0. So it's a very confusing operator. First of all, these 2 equations do not seem to be compatible with each other. And more importantly, this means that D is not a unitary operator because unitary operators cannot kill things. Okay? So we call this a non-invertible symmetry. Okay. Symmetry because it commutes with the Hamiltonian. In fact, it commutes with the full energy momentum tensor, but non-invertible because it kills something.
Just to be sure, all the powers of phi square correlators are 0, or just
yes, all powers. If we put 5, it's also 0. Yes.
if you do this with phi to the 4, or like phi to the 4, phi to the 4, that's not zero.
Oof, that I don't remember. I don't think it is now.
Okay, because I mean, there shouldn't be any other non-invertible guys.
Right.
Roughly speaking.
Yes, so in a sense, you can prove that this is the only non-invertible symmetry of this system. Yes. Mhm.
Interesting. Thank you very much.
Yes.
Is B a linear operator?
Yes. Mhm.
So do you know how D acts on D phi squared?
Not off the top of my head. It's computable, but I don't remember.
Hmm.
So, yeah, it's even, yeah, good point. It's even here, yeah, D of D phi squared is itself.
Ah.
So in a sense, you can think of this as giving this invariant because it gives the sign, but it's, anyway, that's a bit of a formal
But it
manipulation.
forbids the master for
Yes.
high energy if you know people with
Mhm.
highly amusing.
Yeah, but that's what I was thinking of, but phi here is dimension. I know.
Yes. No,
Yes, but
yes.
there's still a hierarchy problem. Why is there a symmetry when you set by the coefficient of phi squared to 0? If there's a quadratic divergence, if you complete the theory.
But this theory should have a whole bunch of phi to the n terms here because it's dimension.
Our coefficient has mass dimension too.
You can certainly add higher
You
monomials
could,
here. I'm talking about what happens when you tune it to 0. If you add those,
So you're tuning all
Yes.
high dimension
Mhm.
terms to 0.
Yes.
Are
Okay.
all of those forbidden by this symmetry? I would have thought like, maybe.
Yes, I think so. Actually, yes, I think all of those are forbidden by the symmetry. So you
Except
naively do
phi
this
squared.
tuning. Okay, and this I think this tuning only allows this.
I think pi to the 8 should
But
fine.
phi to
Yeah,
the
I
8
would
should
have
be
thought phi to
okay.
the eighth and-
No, I'm not sure. It's a little tricky
sure.
because you cannot tell just by looking at it. You need to actually compute things. And I don't remember the answer.
Hmm.
But if you include high powers by hand, you can also tune to criticality and you find similar things. So there's a whole family. These are all the minimum models. The minimum models have lots of non-invertible symmetry. The simplest one only has one, but if you go to the higher minimum models, which come from high dimensional powers, they have more non-invertible symmetry. And some of them flow, like if you flow for a higher minimum model to a lower minimum model, some of the non-invertible symmetries get not. There's a very complicated story there.
Thank you.
No?
And this is it doesn't matter if it's a boson or fermion, but you're in 2D, so maybe it doesn't matter.
So
And in here you have a boson.
what do you mean by bother? I mean,
Boson.
yeah, but I mean there are fermionic theories with similar.
Do this for boson or for.
Yeah. Mhm. Okay. So this is the definition of a non-invertible symmetry. I want to mention that whether you call this a symmetry or not is up to you, but whether there are selection rules is not up to you. It does have a selection rule, so it is something you should consider. Okay. And this is an example in 2D, but there are similar examples in 4D, which some of which have interesting phenomenological applications. For example, there's a similar but not.
Another question, this 0, it's a perturbative 0 or is it a non-perturbative? I mean, this value.
So this is a strongly coupled theory, and it's an exact statement about
It's
that.
an exact
Yeah,
statement.
it's an exact statement.
That non-perturbative.
About the critical model, though. If you change the coefficient here away from criticality, you break the symmetry. So the symmetry only exists at the critical.
It's a non-couple.
But that's why it's a symmetry. It's really a 0.
It's real, it's real.
Yeah.
So in 4 dimensions, there are a few examples that I'm only going to mention super briefly, but if you want to know more, do ask me after the talk. There's a similar symmetry, more complicated in some 4-dimensional theories, and they have been used to explain interesting things. For example, in 4 dimensions, there was a mild puzzle in Python dynamics, and a similar non-invertible symmetry explains the puzzle. That's worked by Zheng and Sharon collaborators. If you go to some natural extensions of the standard model, you find some gauge theory with similar symmetries, and in those theories, you can use a non-invertible symmetry to explain why the theta term of QCD is so small. It is actually odd under the symmetry. So you have softly broken symmetry that makes it 0, and now you have something that is just very small but non-zero. It also explains why neutrinos are so light, etc. So there are some concrete applications of extensions of the standard model that have these sort of symmetries with phenomenological prediction.
Yeah, but those examples again are not continuous.
No, yeah, this is not continuous, this is a discrete. Yeah, so it's just an example of that. Now I maybe I don't know if I sure okay. So this example is a little bit boring in a sense. This is boring. For the following reason. This example has, I told you that it has a Z2 symmetry. And it turns out that if you gauge the Z2 symmetry, this model becomes a free Majorana Fermi. And it turns out that this non-invertible symmetry, after gauging D, becomes just the usual parity symmetry, gamma P, so, which is invertible. It's a regular Z2 symmetry. In this example, the symmetry is non-invertible, but there is an operation that you can do to your theory that makes the non-invertible symmetry invertible. And in this system here, this correlation function becomes just psi bar. And you can trivially see that this transformation here flips the sign of this, and that explains why the correlation function was 0. So in this example, there's a very simple operation that you can do to your theory, where the symmetry becomes invertible, and then you have regular word identity. So we call this a non-intrinsic non-invertible symmetry. Non-intrinsic.
So can I understand it as a, in non-invertible case, there is a topological line attached to an operator, but now you gauge it and it becomes redundant,
Yes.
and you can forget about this
Yeah.
line.
So yeah, I don't want to get into much detail, but yes, that's a way of thinking.
Do we have an inverse mapping between Majorana Fermi and
Yeah, so this is by you can go back and forth. Yes. So you don't lose any information by gauging. You can go solve everything there and go back. And in that sense, it's kind of boring. If you don't want to talk about non-invertible symmetries, you can always do that. Talk about regular symmetry, except the intrinsic non-invertible do exist. Non-invertible do exist. So there are some symmetries that are actually interesting. There are symmetries whose word identities you can never figure out just by looking at regular symmetries. Okay.
Can you give an example?
Hmm?
Are you gonna give examples?
No, but if you look at something like this, you get a more complicated minimal model,
Yeah.
and those you can terminate. So those in those examples, the non-invertible symmetries are intrinsic, but the minimal models cannot do what way. Except for the minimal one.
There's some way to prove that, I guess.
Yeah, it's provable that all those examples are intrinsic, except for this. If you go to the take phi to the so k, this goes to the k minimal model. And except for k equals 2, which is Ising,
Yeah,
the rest are unintrinsic. Yeah.
I see. Oh, beautiful. Okay. I'll have to read about it, but it sounds interesting. I see Fiona looks cool. Yeah.
The definition of non-intrinsic is that there's no representation in which the symmetry is just an ordinary symmetry.
Non-intrinsic means that there is some presentation where it's
Yes.
where it's inverted. And intrinsic means that there is no presentation where it's inverted. Yes.
And does that mean in terms of like just like fermions and bosons, or am I allowed to have?
I don't think
whatever
there is,
be a constrained Hilbert space?
I think anything goes. Yeah, I don't think there's a concrete criterion for when you have one or the other. It's a very case by
You
case.
cannot do any I think there's a statement that you cannot do any topological manipulation to.
Yes.
So I guess I was thinking of like, Majorana chain to like parafermion chain. I want to go to Z3. There's a representation that looks an awful like a Majorana representation of a Z3 plus
So
chain.
I don't know how to.
But I think you're saying that one is intrinsic. That's what I don't understand.
Which one is intrinsic?
So, sorry, I don't know, maybe we should talk after, because I don't want to take too much time.
Okay. So this is what I mean by boring, and sometimes things are boring, sometimes they are not. So here all the examples were discrete, but let's move on to the continuous case, which is the interesting one. There are also boring examples of non-intrinsic, non-invertible. If you look at, okay, we can do something very similar to this. Take the same theory, but instead of a real scalar, make it complex. So now you have a U1 symmetry. D phi where you have a U1 symmetry, which is U alpha phi into the I alpha phi. And there's also charge conjugation, which is phi Adar. Okay, it turns out that if you gauge C, then U1, U alpha becomes non-invertible. This is an example of a continuous symmetry that is non-invertible. And in fact, this example works for anything, not just anything.
This is what Theo did. right?
Yes, this was a super important example for us because we didn't understand anything until we understood this example. Okay. This is an example in any dimension of a continuous non-invertible symmetry, but it's always non-intrinsic. Because you can always ungauge this and go back to the case where it was coming from something invertible. Okay, so this is an example of a continuous non-invertible symmetry.
Is it easy to see that it's non-invertible?
The way you see it is that if you compute the current that generates this thing, the current is phi Adar delta phi. And if you basically if you have with charge conjugation, you change the sign. So under C, J becomes minus J. And so when you gauge C, the current becomes non-gauge invariant.
Mm.
And I mean, there are more explicit ways, but I think I should not go into the details right now.
Okay.
Just take it as a statement.
How do you gauge C?
It's a Z2 symmetry.
Huh?
It's a Z2 symmetry, so you need to do Z2
Ah,
gauge.
So you can just put a
It's the orbital
condition
from
in
string
the
theory.
path integral, right?
Yes, it's the orbital from string theory. You
Okay.
add the twisted sectors and then you project to the invariant states. Yes.
Okay.
Although the details are very subtle.
Yeah,
As Theo
That's why
worked
Theo
out,
wrote the full paper. It was very complicated to get it right. Yeah. So this explains what a continuous non-invertible symmetry is, and I claim that any continuous non-invertible symmetry comes with a twist current. Okay. Now,
So could you please explain in this particular example, why physically we have to gauge C?
you don't have to. I'm telling you, if you choose to do so,
Yeah.
it becomes non-invertible. You don't
No,
have.
but okay, let's just say you tell me to choose
Mhm.
and I follow you. What benefit do you get from
It's a
that?
different theory. You might have some systems
Yeah,
that
but-
describe like this, and
but-
some other physical systems.
Yeah,
that do
I
like this.
understand, it's a different theory because there is a super selection rule, you can never switch from one theory to another, but is there physical examples of this type of theories where you add additionally some super selection rule?
So I don't know any concrete physical theory that is described by the Z2 orbifold of this theory, but
Okay,
this is just to give you an example of
okay.
you know, that these things exist in
Yeah,
quantum.
I understand that by hand you can always.
I mean, in the standard
Put
model-
this limitation, it's equivalent to super selection, either you consider one sector or the other one. And they're non-mixing.
Yeah, so that's why it's kind of boring. It's I'm not doing anything profound.
Okay,
So
okay.
this is just a proof that they exist, not that they're.
But you were gonna say something about in the standard model.
I was gonna say that in the standard model, we don't even know the gauge group. We know that it's like SU3 plus SU2 plus U1, but it might be mod Z6 or not, maybe mod Z3 or Z2. We don't know if there's a similar gauging in the standard model, so we have to consider all possibilities. And these are different theories with different predictions. So whether it's just a generalization of it. And when you do discrete gauging, you might also make things that were invertible before become non-invertible afterward. So
So
that's something that-
if you do this and consider all three versions. Extract predictions,
Mhm.
can you compare them with
Mhm.
experiment?
Sure.
So which one is better fits experiment?
Nobody knows, no. You need, no.
Nobody knows for
Why
now,
is that?
because the predictions are hard to actually physically measure.
They only differ in
But
very,
a question for
very.
Tony or Zheng or somebody else.
So
It's a big open problem.
how to measure these different, how to distinguish these different theories?
Do any of you want to comment before I accidentally say something wrong?
to my understanding, I have to always attach new gradient to the standard model to test them. Either I have to find particles with non-fractional charge to realize this, or I have to have axial strings and I measure the phase when the charge particle walk around it.
Yeah, these different,
I always need something
yeah,
else.
these differences don't affect like standard model processes themselves. But they affect if you try to add something to the standard model, it can really change it. It can really change what you're allowed to add.
For instance, axial domain wall,
Yeah.
would it change?
I personally don't know, but it can affect guts. It can affect
It
guts.
affects guts, it affects
Yes.
guts,
Okay,
the way this is embedded.
okay.
But I think it's supposed to also affect some physics of axions. I've heard some who talking about
Yeah,
some wrong,
yeah,
but
the
I'm not
phase,
confident to summarize it, so.
Yeah, so standard model do not distinguish them.
So for the time being, we may be safely leaving it just a standard model, right? Okay, thank you.
So now I'm gonna get abstract for a few minutes. I hope you bear with me. If you don't care about the more abstract parts, you can forget. I'm gonna go back to tangible things after that. But I wanna give a quick sketch of this theorem here. How does the Noether theorem generalize for the case of twist things, okay? And again, I'm gonna talk about any dimension, but I'm gonna restrict to CFTs because that's the case I really understand. So the claim is that if you have some non-invertible thing that I'm gonna call D out, which is continuous, it depends on a continuous parameter. This implies the existence of a twist current, and vice versa. Okay, and I'm gonna explain the two arrows separately. One point that is kind of tricky is to define what we mean by continuous symmetry in the first place. Everyone knows here what a continuous symmetry is, but how to define it properly is actually quite tricky. Because if I take, for example, the alpha, and I write, for example, the identity plus alpha times charge conjugation, this depends on a continuous parameter, but I wouldn't call this a continuous symmetry. Continuous symmetry is something that depends on a continuous parameter, but in a non-trivial way. And how do you define non-trivial? Okay. So the definition that I'm going to be using of a continuous symmetry, whether invertible or non-invertible, the same definition works for both. It is borrowed from the condensed matter literature, and I'm going to say that D alpha is a continuous symmetry if and only if it admits an exactly a marginal deformation. Okay. In CFT, a deformation, in QFT, a deformation is something that you can change your theory by. Marginal means that it's that the dimension of your deformation is exactly whatever it is, even in a dimension, like D minus 1 or whatever. Okay. So this is my definition. It's a little bit abstract, but it turns out that you need something precise, otherwise you can't even talk about these things. Okay. So
how does it work on the pre-scalar example? Or sorry, the complex scalar? That's what I mean. Where is the marginal deformation?
So in CFT, you have the unitarity bounds that tell you that for a vector operator, for a vector, the has to be 1. The dimension of the operator has to be larger or equal to D minus 1. This is the unitarity bound coming from unitarity in CFT. And equality, if and only if, it's basically if it's conserved. This is a statement from CFT. So the
yes, that's fine.
You're okay with that? Okay. So exactly marginal in this case, let me not say exactly. Marginal means that the dimension is exactly D minus 1, and that means that the union of the operator is so being marginal.
Why are you defining marginal this way?
Marginal means that the dimension is whatever it needs to be. So
sorry, I had this, sorry, I'm probably something very stupid, but I thought a marginal operator is a thing you can add to the Lagrangian, which has a dimensionless coefficient, and that is
Yeah.
not the condition.
Yes, so
So what do you mean?
because I'm using the CFT definition, which is an operator that lives on the defect. So it's you have to compute the scaling dimension with respect to the manifold where it lives.
So it's marginal with respect to defect CFT, not the CFT. Because in the
Yes.
CFT, there's also
So-
marginal deformations.
So
There's a space of conformal manifold, whatever, conformal manifold, so that's not what you
so
said.
here I'm talking about zero form symmetry,
Yeah.
zero form, which means that the alpha is the dimension is d minus one, right?
That's right.
And so it has to be marginal with respect to this.
Could you please kindly repeat the same thing? Not necessarily, conformal symmetries are very special. Let's take any symmetry you want, let it be weakly coupled, so. And could you please tell me what in this case is this non-trivial continuous symmetry?
There is no definition in non-CFTs. I don't think there's a precise definition of a continuous symmetry and non-CFT. That's why we need CFTs. We
So
don't,
it exists only in CFT?
no, a precise, rigorous definition only exists in CFTs. In
Yeah,
non-CFTs, we believe that everything should work.
You're saying you don't know, so maybe can I suggest that the change in emphasis? You don't know a precise definition of non-CFTs, but you're probably not saying that one doesn't exist.
Yes, exactly.
okay.
We don't know how to define these things.
Okay, but tell me some kind of non-precise intuitive definition. Take any theory you like, except conformal.
Well, I mean,
What do you think in this
the
theory?
intuitive definition is that the intuitive definition
Yeah.
is that a continuous symmetry is some family of symmetries that depends on a parameter that you can change continuously. That's the definition of a continuous.
Okay,
The problem is that I don't know how to write down in mathematical terms. I don't know what it means to have a family that is continuous. Because this is a continuous family, but I don't wanna, I do not wanna consider this as a continuous symmetry.
I understand.
So I don't know how to rule this out in a precise way, except in the conformal case in which I can use this definition to rule it out. Okay?
So you need a symmetry which is broader than usual,
Yes.
and it has an internal parameter,
Yes.
which basically it's, in usual cases, continuously many symmetries, that's what you have. Usually no reason, no natural theories might have that. Because probably in this case, S matrix will be trivial, right? If you have continuously many symmetries,
No, I mean, you want symmetry. Just
U1 is just one symmetry, right?
no, it's continuously many because you can rotate by any angle.
Yeah, it's a continuous, it's U1, but nevertheless, you have only one current which corresponds to
Yes,
U1.
Yes. Mhm.
So in this case, which you want,
It's the same thing. I'm not I'm considering the exact same thing. I'm saying that a U1 symmetry,
yeah,
a U1 symmetry is a continuous symmetry.
Yeah.
We all agree on that. But how do I prove that? I only have the proof in the conformal case. I don't know how to prove it in a non-conformal case.
Okay.
This is a technicality. It doesn't matter.
okay.
Not proof,
Okay.
definition.
It's a matter of
You
definition.
have
If I
good
want-
examples like Lie groups,
Yes,
right? They're like
that's a
good
continuous
continuous
symmetry.
symmetries. So
I don't know how to.
So any basically continuous symmetry which we dealt with usually.
Everyone knows, yeah. We all agree what a continuous symmetry is. I want the
It
definition.
works for you, right? For this
Yes.
purpose. Okay.
I want the rigorous definition. We all know intuitively. We all
Okay,
agree.
forget about rigorous definition.
When I have a theorem, I want to prove a theorem. So for a theorem, I need a
Okay.
definition. That's why I said this is kind of an abstract part that is kind of boring. and you
He
can-
wants to make a non-invertible version, that's why.
He wants to make a non-invertible version.
Okay.
That's why he wants to be careful, yeah, he wants to be careful because it's about to get tricky.
Yeah.
Yeah.
The question.
Well, the question, why can't we just take that as a definition? I mean, partial J is zero. I first define a current and then integrate it and then I get a topological.
So you're already assuming Noether's theorem. I don't want to do that. I don't know if there's a current yet.
I'm going first to define the.
I want to prove Noether's theorem. So I need to define both separately. Yeah. In order to prove the theorem, I need to define this, and then show that they're equivalent. But I don't know that yet. Okay, so this is my definition. To say, so, sorry, the definition of marginality in general is that this is what it means to be marginal, right? For
Yes.
but now the deformation lives on a d minus one dimensional line, so that's why I'm claiming that marginal with respect to that deformation. So sorry, what is this deformation even? Like, what am I talking about? What I mean here is that if I have a family of operators, I can go from alpha 1 to alpha 2. So I need to be able to deform this family. So this deformation is precisely what generates the change in alpha. So if I have d alpha and I want to go into d alpha plus some small delta, I do that by turning on this deformation on the defect. So I have a defect, I can turn on the deformations on the defect, and that deformation is what generates shifts in output.
So, okay, excuse me.
Go ahead.
Okay, take VCD-like theory and take the number of flavors very large, but still in the asymptotic freedom domain. So where you're inside conformal window, at least it's in the infrared, the theory is conformal. So how would you apply your definition to this particular theory? What do you request or demand from this theory to
So
be?
you can go to Bank-Zaks, for example, which is
Yeah, Bank-Zaks.
this theory has some operators. It has operators J-nu, right?
Yeah,
Which are the currents that generate the symmetry. And if you compute the dimension, you get this dimension. So these operators are marginal. And
Okay.
that's the CFT definition of why Bank-Zaks has a continuous symmetry.
okay.
It has symmetry because it has these operators.
So these are flavor sigma.
In that case,
Yes.
yes.
Yeah.
In that case, yes. Can I just check my understanding of where you're going to use this?
Mhm.
You're basically going to assume that there exists an operator, which is a vector operator with dimension d-1,
Mhm.
and then you're going to show that it must be conserved, and therefore it's an Noether current.
No,
Is that-
if dimension is strictly d-1 with all interactions included, it's almost automatically. Conservation is at least in one.
I also think
yeah.
so, but that's what I think
Okay.
Diego is gonna tell us, yeah.
So the first arrow, once you have a precise definition, the first arrow is completely tricky. Because
Yeah.
the alpha is continuous, it means that it has an exactly marginal deformation by definition, and that deformation is defined. So if you assume that D is continuous, that implies the existence of some deformation that I'm gonna call J, because I know what it is. That implies the existence of a deformation, and it's marginal by definition, so that means delta of J is d-1. Okay, so at this point I cannot say much more. But if I also assume that the alpha is Lorentz invariant, it commutes with Lorentz transformation, then that further implies that the spin of J is 1, and now we're done, because these two equations together, spin equals 1, delta equals d-1, these two imply that the mu is 0.
Okay.
So it's a triviality. I'm not saying anything deep, but I need to have a concrete definition in order to prove it.
But then if you did this for the axial current, it wouldn't work.
No, because the axial doesn't have
Of
a.
course, yeah, of course, but that means then that, is there gonna be a non-invertible version of the axial current?
We hope so, but we have no idea.
But that's kind of what you're alluding to, potentially.
We would like to claim that yes, but we don't have any evidence for nor against. So I don't want to make any claims about it. Okay, so this arrow is trivial, just follows on by definition. Now I'm gonna describe the other arrow. Okay? One thing that I didn't say here is whether this is invertible or not. This story is true both in the invertible and the non-invertible. So everything that I wrote here is true. The only difference is that the deformation that we're talking about is something that lives on the defect. It's not in general a bulk operator. This only proves the existence of some current J that lives on the alpha. So this proof doesn't tell you whether J is a true bulk operator or it's only defined on the defect. Okay, and the other claim is that J, you can take it outside of the defect, so it becomes a regular point operator. So this is a bulk operator if the alpha was invertible. So if the alpha is non-invertible, then J must stay on the
So you're basically considering more than I just got. So you consider some bulk space time, right?
Mhm.
And then some topological defect on it.
Which is codimension one.
Yeah, okay, which has codimension one. And then you are interested in the symmetries on the wood volume of
No,
this
this is the
topology.
symmetry.
Ah,
The defect is the symmetry. This is the thing that generates the symmetry.
yeah,
This is the symmetry. This is the symmetry.
in the bulk.
Yes, it's a box. Yes, it's a symmetry of the box. Yes.
Okay, and then why do you say that it is one, I mean, when you said consider the one which is lives only on the defect, topological defect, so
So it's
this
similar.
symmetry should be also on the topological.
So this is similar to the Wilson, the Wilson loop that I was talking about at the beginning. If you have a young Mills,
Yes,
then the field strength lives on the Wilson line. You cannot take it outside. So it's something that is stuck on the Wilson line. In U1 is different. In U1, F mu is bulk. It's a bulk operator.
why can't you take F menu is?
It's not gauge invariant.
Ah,
It's not gauge invariant.
okay.
So it's not a bulk.
Given confined, but you can.
No, it's not about confined. Doesn't matter if the field confines or not.
Okay, it's
It's-
gauge.
It's gauge invariant.
Yeah,
So some operators are only defined when inside some other extended things, and some operators are free to be wherever they want.
so F menu is squared, let's say, it's okay.
That's a different operator.
It's the
yes.
bulk operator.
That's a different operator. Yes. F
Okay.
itself,
If
it's-
you want to define F menu, you have to attach some defect to it,
Oh, which one?
string, yeah, or line or whatever.
so the claim is that if you have a non-invertible, if you have a general symmetry, doesn't matter if it's invertible or non-invertible. If it's continuous, then there is some current. And then if the symmetry was actually invertible to begin with, then that current is a regular operator of your field. It's just a bulk thing that you can
Okay.
do whatever you want. But if the symmetry was non-invertible to begin with, then the current only exists on the diff. It's not something that you can take outside it.
So it has something to be attached to. In the same Banks Zach's example,
That's a invertible regular, it's a regular invertible symmetry, so the current is a regular bulk thing. You
Okay.
don't have to attach to
but,
it.
okay, Banks Zach's is the conformal regime, so you can consider F menu, right? Outside.
Yes. No, you can consider it, yes, but it's not a current, it doesn't generate a symmetry.
It's not a current, no, it's not a current.
Okay, listen.
Yes, sir. Can you please explain? I didn't follow the argument, why is the spin equals to one?
That follows if you assume that the defect commutes with Lorentz transformations. Not every defect commutes, so this is not completely general. There are other things that could happen. For example, a translation is generated by the energy momentum tensor, which doesn't have spin one, has spin two, but a translation doesn't commute with Lorentz transformations. So the claim is that if your symmetry commutes with Lorentz transformations, then the spin must be one. That's not obvious, like there's I would have to spend like 10 minutes proving that, but
No, that means that symmetry basically is symmetric transformation by
Sure.
itself is scalar with regards
Yes.
to law.
so everything here is intuitive. I'm
Yeah.
saying if you want to prove it rigorously, it's not obvious, but yes. So the spin of the current is fixed if you assume that it's Lorentz invariant. If it's not, then it's not spin one, it could be whatever.
So it can't just be a scalar, spin zero thing?
No, if you assume Lorentz invariance, no. If you don't care for Lorentz invariance, I don't think it could be spin zero. I think that would violate unitary bounds, but I'm not entirely, so we'll have to think about it. Okay, so this is this arrow here. Everything I said was kind of not trivial, but if you want to do things rigorously, you have to define these things more precisely. Now let's do the opposite arrow, which
Typically currents have spin one, right? J mu has one logarithm.
not typically, always.
I mean, yeah. So it's not surprising, but
No, nothing that I said here should be surprising, yes.
Is it supposed to be obvious that if the GA is non-invertible, then you are forced to keep your J on line? or-
It's not obvious,
It's not,
no.
okay.
So, and maybe I can give a sketch of an argument. So if you have, let's say that this is the L, right? And I told you that there is a current that lives on the defect, and you cannot in general take it outside. Now this is topological, so I can move it around as much as I want. So I can do this. And now I can collapse. So what I get, basically something like this. This is equal to this, this is equal to this. Where here, what I have is basically D times D bar, right? Because if you look up and above,
Yeah.
if it's invertible, this is
That's fine.
goes away and you got a range of things.
Okay, but precisely that fails if it's not invertible.
Yes.
That's the point. That's beautiful.
And so if it's non-invertible, this is gonna be some non-trivial line. And now you can see the branch cut, that's the branch cut base.
Yeah.
So that's why J has
So
a
that's beautiful.
branch cut in general. Now for the opposite arrow, again, it's gonna be kind of, it's gonna sound like a triviality. But once you have the correct definitions, things should be trivialities. So let me explain the other arrow. So now what I wanna do is, I assume that there is some current with spin 1, dimension d-1, that lives on something because it's twist state. So by definition, J is a twist current, so it lives on some topological defect, on some B, I'm gonna call. And I wanna prove that this implies the existence of a continuum of a continuum of defects that are all symmetries. Okay? So I'm gonna explain how that error works. And so again, I'm gonna borrow things from CFTs. If you have something that is marginal, you can just turn it on and that gives you a deformation, right? Okay. So I need to find some B that has J as its marginal deformation. So the definition is kind of obvious. If you have, I'm going to define B alpha with whatever insertion that you want to do here as the path integral phi E of, I'm going to insert B and then I'm going to do E to the minus S phi plus alpha, the integral of J. Okay. Now, this defines the defect D, and let me say that first of all, it's well defined because I'm integrating J only where I'm putting B. So I'm taking D to B. Let's put it on some M D minus 1 dimensional manifold. Then I'm going to put B on the same M D minus 1 dimensional manifold. And I'm going to integrate over the same D minus 1 dimensional manifold. So the base where the current was defined to begin with is the same thing that insert here, and it's the same manifold where I integrate. So this is a well-defined thing. I'm not integrating J away from the base where it was gauging very quickly. Second of all, alpha. This is exactly marginal. So D is topological because alpha was marginal. Right, assumption. Okay.
So sorry, so D acts on 3 dots, and this
Here
dots
is
also
answer.
should be.
Yes. So here is whatever functions of your fields you wanna insert here. Okay. So this is in the condensed matter literature, this type of deformation is called a pin and field deformation. And you can do that for any alpha, doesn't have to be marginal, but when it's not marginal, this defect is not topological. It's going to be some conformity. But when alpha satisfies this condition here, that the dimension is marginal, again, with respect to D minus 1 dimension, then the whole thing is topological. And it's also Lorentz invariant. Because let's see. Okay. So this is a Lorentz invariant combination of
Yes,
okay.
and this contour belongs to B. Yeah, and why then it's not 0? Because it's the integral of the derivative for.
There's no derivative. So sorry, just to check. So it's you're just
J mu
it's
dx.
J mu dx mu, but
Yeah.
that's the contour integral. It's not.
Yeah,
Yeah.
understand.
And sorry, Diego, are you going to give us an example of an intrinsic continuous non-invertible symmetry?
It depends how if I should stop now, I guess.
Well, we had a lot of questions, so maybe we could hang on for maybe 5
I think we should hear it. Yeah,
Yeah.
people need to flee. Of course, you should flee, but
Yeah.
I want to hear an example.
Yeah, so
Okay, so this is
So does that mean the deformation in the in the exponential, it's only there when we are living on B. Outside B, that term should be 0.
Well, I'm integrating only on the manifold where I'm putting B to begin with. So it doesn't matter what J does away from B. I'm not even integrating that. So for this, in this construction, the only thing that goes into the formulas here is what happens on B. So what happens away doesn't matter. Anything else? Okay, so this is a generalization of Noether's theorem, because now if J was supposed, it's a bulk thing in the first place, that means it's not attached to anything, and you can take B as the identity, and so you just remove B from there, and you have the normal expression for another term. Okay.
And you think that we're living in our 4D space-time, we're the defect and there's a fifth?
Yes, maybe, I don't know. So this is the abstract definition. You can also give a definition of the alpha in terms of the usual, like a series up and something here. I'm not going to read them, but there's a similar definition, and you can use that if you prefer that definition. So if you want examples, I can only give you examples, interesting examples in 2 dimensions. If you go to 2 dimensions, then delta has to be 1 and the spin has to be 1. And that means that the conformal weights have to be 1, 0 or 0, 1, which I'm not going to discuss separately. So if you go to a 2-dimensional CFT and you find any twist operator that has this specific dimension, then your theory has a non-invertible continuous symmetry. Okay? That's the claim in 2 dimensions.
Non-invertible?
Well, a continuous symmetry, which may or may not be invertible, depending on whether that operator is attached to something or not. So you consider the set of all, you take any line here which is topological, and any operator here. Oh. Now, if H of O is 1 and H bar of O is 0, then you have a continuous symmetry, which is invertible if L is identity and non-invertible. L is not invertible.
What does mean L1?
Identity.
If you could delete the line, if the line is deletable,
L is
L is the line.
L is the line.
L is relevant.
But I'm sorry, this sounds like it's a distinction between whether this operator is in the twisted Hilbert space or not.
That's why I call it a twist.
But yeah, indeed, but then it sounds like I could manipulate as to whether it's there or not by playing with gauging symmetries. So so then it doesn't sound like it's going to be intrinsic. So
Well,
what am I missing?
Is there some gauging that makes L into the trivial line or not?
Ah, okay.
Sometimes there is no gauging.
Okay, fair enough.
So that's precisely, that's a great point. So now we have a concrete criterion for whether a given non-invertible symmetry is intrinsic or not.
I see.
You have to ask. So if I give you the alpha and I ask you, is this intrinsic or not? What you have to do is find some discrete gauging. That makes the line L into the identity. If you find that gauging, then the symmetry was non-intrinsic. If you do not find the gauging, if you prove that no such gauging exists, then your symmetry is intrinsic.
Does it have to be a discrete gauging? Could it be some interesting version of a continuous gauging?
The problem is that those are not general. You're gonna go back and forth. Gauging in one symmetry.
Let's talk later because we have some.
Okay, if it's we wrote that if some maybe flat gauging is something that one should.
There's something,
but
okay,
but
there's a
yes,
long story that we should go
Right.
through together,
Yes.
that Maria, she and I worked out, okay.
I have a question.
Yeah,
So
please.
I know we are talking about safety, but your construction reminds me of something in the integral model,
Okay.
like the bounding group construction in the.
Yes, that's yeah, indeed. So that's one of the open questions that we have in the debate.
Okay.
This is all very reminiscent of that story. We don't know how to make the connection precise. Like everything sounds extremely similar.
Yeah, because we can just treat a sine bond like a perturbed CFT, right? So
Yes, so we don't know how to make it precise. Yeah, in this.
we can discuss it later.
Can you give a concrete example of where it is impossible to find this discrete gauging to?
Yes, so
Yeah.
the problem is that in order to prove that something is intrinsic, you have to prove that no discrete gauge exists, including non-invertible gauge. So you can gauge something is non-invertible, but
Yes.
and in order to prove that, first you need to classify all possible gauges. If you don't know all the gauges, you cannot prove that.
I don't know how to prove that.
No,
I'm asking you.
There is no theory except the minimal models where all of the symmetries are known.
But, okay, is there a minimal model example that you can give?
No, minimal models do not have continuous symmetries, neither invertible nor non-invertible. Minimal models do not have
So
this.
does it mean that you don't know an example, which is
We have
definitely
something very close to an example, which I'm
Okay.
gonna tell you now. If I have 5 minutes.
Yeah, from my point of view, yes, but if somebody has to leave, then please leave. You know, it's okay. But I feel like we're getting the punchline. That's why I'm like,
So in order to find examples, you need to find twist things with these dimensions. You can go through your favorite list of two-dimensional CFTs, minimal models. No, there's no such thing in minimal models. So minimal models do not have continuous symmetries, neither invertible nor non-invertible, neither intrinsic. There's nothing there. C equals 1, so free boson. Yes. There are operators of this form, but there are always non-intrinsic. For all of them, you can find what the gauging is that makes it invertible. And the
What
list
is
of
non-INT?
non-intrinsic.
non-invertible.
It's in this boring category that you can always.
Yeah.
And the next example is WZW. Here we have many examples of non-invertible symmetry, non-invertible. And we believe that they are also intrinsic. So maybe I can give you a concrete flavor of when you made this. So take SU2 level K, which is the simplest WZW. So we know that there are non-invertible symmetries, and we have the full list. It's like 4, 8, no, 4, 10, 18, 20 something. There's an infinite list of levels that have conserved currents. So for all of these, there's a non-invertible symmetry. And when K is 4, then I'm connecting. There is some gauging that makes it invertible, where it's non-intrinsic. For everything else, we don't know, but we believe it's intrinsic. And let me tell you why we think that. Or rather, let me tell you a slightly more modest goal, which is the following. Instead of trying to look for all the gauges that one could do, I'm only gonna look at gauges that commute with the SU2 flavor symmetry. If you look at only gauges that commute with this symmetry, you can prove that no gauging exists. Okay, so that means that the flavor symmetry of the system, symmetry, is the non-invertible symmetry, that's the SU2 symmetry. And if you wanted to make this invertible, we don't know if it's possible or not, we don't think it's possible, but if it was possible to make this invertible, you would have to gauge something, make it invertible, but you lose this. So if it was possible to make it invertible, you would have to give up the SU2 symmetry. So if you want to write down selection rules for the SU2 theorem, similar to the one that I gave in the IC model, if you want to write down selection rules for both symmetries at the same time, then this must stay non-invertible. It might be possible to make it invertible, but only at the price of giving up this symmetry. So if you want to have selection rules for that include SU2, then this must stay non-invertible, because it's conditionally intrinsic, and we believe it's the best you can do if you don't know all the symmetries. And we, except for the minimal models, we don't know all the symmetries for it. So I think that's all I have for you. Thank you very much.
Okay, you can ask more questions, but our speaker did not have lunch yet, so.
It's fine.
Okay.
So in 4D, is there any example in 4D?
We have examples, but they are all non-intrinsic. We don't have any example of something intrinsic. So for example, the complex scale would be phi squared this has a regular Yunqin symmetry and charge conjugation. But if you gauge charge conjugation, then U becomes non-invertible. This is a complete example in 4 dimensions, but it's non-intrinsic. So this is something that is known in 4 dimensions. But examples that are intrinsic, no.
So for free field theories, there are not so many conformal field theories in 4D, right? N equal 4, super Young needles. It's probably the only example.
Okay. The good news is that despite conformal symmetry playing a prominent role in the technical construction, the basic idea, the basic statement doesn't rely on conformal symmetry.
That's the
So
hope.
it
I don't know if there's some
probably is
subtlety.
general. I don't know, it's a guess.
Hmm.
Sorry. to jump in.
Yeah.
Okay, so maybe we should end there for now.
On an
So
optimistic
thanks,
note.
speaker again. For dinner, we're gonna go to tea house, leave at like 5:45. So if you want